This is a video on section 1.8, some more limit problems that explore a couple different techniques. So sometimes solving a limit problem can combine techniques. Okay, we can combine, say, graphical and table of values techniques. Okay, and oftentimes this combination of techniques really helps when you're dealing when you're working with functions that contain the absolute value of a function. The absolute value of x, or absolute value of x minus 2 is in this case. So I just want to do a quick review of the absolute value function, and remember that the absolute value of x, one way to define it, and I think the most helpful way, is that it's the value x when x is greater than 0, and it's negative x when x is less than 0. So this definition, this is a piecewise defined function, is consistent with, for example, when you say take the absolute value of 4. Notice that 4 is greater than 0, so according to this definition, since x is greater than 0, the number that you put into the absolute value, the value of the function is just the value of x, so it's equal to 4. But if you take the absolute value of, say, negative 5, according to this definition, negative 5 is less than 0, so you get kicked into, since x is less than 0, you get kicked into here, and you're supposed to take the negative of the value that's in there, so you get negative 5, which is positive 5. So it has the end result of making whatever was inside of it positive, but it does, the definition does that by introducing a double negative. Okay? So what about, for example, if I ask you to compute the limit as, say, x goes to 0 from the right of x? Okay? Keep in mind that as x goes to 0 from the right, that means that we're creating a table of values. Oh, I'm sorry, this is an absolute value of x. A table of values for x getting closer and closer to 0, but from the right, so we're looking at numbers like 0.5, 0.1. Okay? And when you compute the absolute value, since these numbers were positive, the absolute value is just 0.5, 0.1. And we're getting closer and closer to 0 from the right. Okay? So you had a table of values there. Okay? If I asked you to compute the limit as x goes to 0 of the absolute value function, you could complete the other part of the table and then see if the left and right limit were the same, and then you could say what the answer was. Or you could create a plot of the absolute value function and plot this around 0, which was the point that we're interested in. Here's a graph of your absolute value function. As x is getting closer and closer to 0 from the right, you can see our values of y are getting closer and closer to 0. As the values of x get closer and closer to 0 from the left, we can see our function values, our y values, getting closer and closer to 0 from the left. Okay? So according to the graph, the limit as x goes to 0, both left and right limits are equal to the same thing, so they're both equal to 0. And therefore the limit as x goes to 0 is 0. Okay? How does that jive with maybe a more complicated question involving absolute value? What's the limit as x goes to 0 from the right of absolute value of x divided by x? Okay, is this possible? Okay, notice that this function f of x is the absolute value of x divided by x. does not exist at x is equal to 0. So you can't just plug 0 into this function. We have to be very careful about doing the limit problem. Okay. Now, one could create two techniques. One could create a graph, or one could create a table. Okay. Let's take a look at the table. Okay. Let's create a table of values for the absolute value of x over x. And we're concerned with the value x is equal to 0. But remember, that function does not exist at 0, so we can't use that to evaluate the limit. As x gets closer and closer to 0 from the right, okay, that would be 0.5, 0.1. Okay, notice what happens when you put in 0.5. It's the absolute value of 0.5 over 0.5. The absolute value of 0.5 is 0.5 divided by 0.5, and you get 1. How about when you put in 0.1 into the function? Absolute value of 0.1 divided by 0.1 is equal to 1 also. So the limit as x goes to 0 from the right, as you get closer and closer to 0, it looks like our values are going to be 1 for no matter what value of x. Okay, from the right you get 1. Okay, and if you did a graph of that on your calculator, the absolute value of x divided by x, right, you can see this on the graph. As x gets closer and closer to 0, the values of y are always equal to 1. There is a horizontal line here. Okay. So the graph of the absolute value of x over x function is not defined at 0, and it's equal to 1 for all values of x greater than 0. Right? What do you think about the limit as x goes to 0 from the left of the absolute value of x over x? Okay. Let's create a table of values. How about 0.5, 0.1? Negative 0.5 and negative 0.1. We're to the left. We're to the left of 0. So the absolute value of negative 0.5 over negative 0.5. The absolute value, since negative 0.5 is negative, we have to put the absolute value says that that's negative 0.5, and 0.5 is already negative. So that would be 0.5 over negative 0.5, which is equal to negative 1. And when you put in negative 0.1, you will also get negative 1. So this function is negative, and it's undefined at 0. So it's negative 1 when x is less than 0, and the function is positive 1 when x is greater than 0. So the limit as x goes to 0 from the left of this function is negative 1. Okay. And therefore, those two limits are different, so we say that the limit as x goes to 0 of the absolute value of x over x, that limit does not exist. Okay, because the left limit and the right limit were different. Okay, so that should be a good problem for combining graphical and table techniques. Okay, so ends this video.